Welcome to all. Let us continue with the next concept. So that is universal gates. So you have a concept called boolean gates, isn't it? So and or operation boolean functions. I have already uploaded that particular video some week back. So where you have seen that truth table xy, if the input is two inputs, if you have x and y, then what will be the result, and what is and gate, not gate, all the gates, logic gates you have already seen, isn't it? And using that gates, how to build the circuit also I have shown, isn't it? Now it is now the concept is universal gate. Okay, so here what you mean by universal gate, and how exactly you can build some universal gates, we will see here. Universal gate is a gate which can implement any boolean function without a need to use any other gate types. Okay, that is the thing. So if someone asks what is universal gate, then you have to say that you should be able to implement any boolean function. Actually, it is not just the particular function. It may be any boolean function you should be able to implement, and you should not require any separate gates or any gate type. Okay, that is called universal gate. The NAND and NOR gates are universal gates. Okay, in practice this is advantageous since NAND and NOR gates are economical and easier to fabricate, and are the basic gates used in all IC or integrated circuit digital logic family. Okay, so in IC digital family, now because in so many circuits we will find this IC, isn't it? So we can implement NAND and NOR. Okay, so not of and not of or, isn't it? NAND gate and NOR gate. Okay, we can implement in almost all the digital logic families. Okay, universal means you can build every possible logic function with all NAND gates or all NOR gates. That is the thing, you should remember this. Okay, now you can see there logic function and symbol and circuit using NAND gate they have shown in that image. You can concentrate on this. Now see, so you have inverter, and you have and you have or function, and function, inverter function, and or function. Now if you look at inverter function, so what is the symbol? It is just not gate, isn't it? So if the input is a, then you should get the output as a dash, or if the input is 0, output should be 1, or if the input is 1, output should be 0. It is a complete ulta. That's the same inversion, or not gate. Next, after that, how can you build using that circuit using NAND gate? You can see how exactly you can build the NAND gate here. So it is a, you are giving a two inputs, isn't it? Because see, you can see a is given as one input, and from the middle of that line you are pulling one more line and you are giving the input to that NAND gate. So and followed by not, isn't it? So normal AND gate, and you have one bubble that represents and plus not, that is nothing but NAND. Okay, not of and. So ultimately if you get two A's, so a into a, ultimately a into a, then you are going to get, if you whatever the answer you get, you are going to not it. So that time you get the answer as a dash. Okay, so a into a you will get, so a naught is a dash, something like that. Now you can see and function. So when you have a and b, and a function will what it will do, it will just multiply. So you will get the output as, or result as, a into b. Now when you use NAND gate to represent the and function, how can you do that? So you can do that like this. So you have to input a and b, you are giving that a and b to NAND gate. So NAND gate will produce one output. That output is given twice to the again a NAND gate. So ultimately you are going to get the value as y, or you are going to get the result. Ultimately what result you will get? So a into b, whatever the answer you get, it is y naught, isn't it? So if you consider result as a y, then a into b, and whatever the answer you get, you have to not it, you are going to get one result. That result will be fed to another NAND gate twice, isn't it? That's why, see, after the output of that first NAND gate, you are bringing down another line from that. So output line, so two outputs, so same value will be given twice to another NAND gate. So that NAND gate will produce the output as y. So you can build that circuit in that fashion when the logic function is and. Now when the logic function is or, how to do? So if the normal symbol is a b, so ultimately you are going to get the value as a plus b. Now how exactly you can do with the NAND gate? See, you have 3 NAND gates, isn't it? The first NAND gate you are giving 2 inputs A. For the second NAND gate you are giving 2 inputs B. Now A will produce Y dash and B will produce the output as Y double dash. Okay, just for the representation. Now you are giving Y dash and Y dash to again one more NAND gate, and you are going to get the value as Y. Ultimate result will be Y. This is how you can build, actually you can build the circuit using NAND gate. Ultimately you have to get the value output as Y. So that is the reason how you can work on it. Okay, this is how you are going to work on NAND gate, or you can build the universal gate. So this is a small concept actually. Ultimately, if someone asks what is NAND gate, so you should say that any boolean function or any gates or any logic gates or logic function should be able to build using NAND and NOR gate, and without using any separate gate type. Okay, so that is nothing but universal gates. Now the next concept is simplification of boolean function. Okay, how can you simplify the boolean function? So you have one method called map method in simplification of boolean function. So whenever you have some boolean functions, how exactly you can reduce it, how exactly you can simplify it. Okay, see, these are the some of the practical examples you will get here. Practical questions will be there, like they will give their own boolean function and you should be able to reduce it. Now how to reduce it we will see. So you have one method called map method. Okay, now we have simplified the boolean functions using boolean postulates and theorems. So previously in the previous slides you have seen there are some boolean postulates and some theorems were there. So using that postulates you were proving the theorem. It is something like A plus A dash equal to what, A into A dash equal to what, isn't it? So you will be having some postulates. Based on that postulates you try to reduce the boolean function. Now using map method, how can you do, we will see here. So what are the issues? So it is a time consuming process, isn't it? You have to remember the postulate. You should, I'm not saying you have to by heart, but definitely you should keep those postulates in your brain, isn't it? Because otherwise it is not possible for you to solve it. I am not saying that it is not required. It is definitely required, but it is a time consuming process, isn't it? So to overcome from that, we have came to this particular thing, map method. Okay, now they have given one more point there. We have to rewrite the simplified expression after each step. You see, you have to consider each step there, because in the marks, if the question is asked for final exam, so each and every step will be counted, and each and every step will carry some marks. Okay, but that is the reason why it is time consuming, as well as you have to rewrite the thing. So it is a double work, or it is a burden, isn't it? To overcome from that difficulty, so that Carnot, it's a Carnot map. We have also say Carnot's map. So Carnot introduced a method or for simplification of boolean function in easy way. Okay, so this method is known as Carnot's map, method, or K-map method. So K-map method is very famous. That terminology is very famous. So K-map method, it is a graphical method which consists of 2n cells for n variables. So if you have n variables, then the number of cells will be 2n. So you have to twice it, you have to double it. The adjacent cells are differed only in a single bit position. So ultimately that bit position or number of bits you are going to pass for that particular position. So this is one of the important thing you have to remember. So when you have 2n cells, n variables are possible, and adjacent cells are differed only in a single bit position. Okay, now K map for 2 to 5 variables they have said, but ultimately in your syllabus you are considering only 2, 3 and 4 variables. Okay, now K-map method is most suitable for minimizing boolean functions of 2 variables to 5 variables. Now let us discuss about the K-map for 2 to 5 variables one by one. So that 5th variable I am not considering. Up to 4 we will see, because in your syllabus also you have that much concept. But once you get the idea, then it will be easy for you to continue with that particular method. Okay, now mainly why you are using K-map? So K-map can be used for minimizing the boolean functions. Okay, now 2 variable K-map. Let us see how 2 variable K-map will work. The number of cells in 2 variable K-map is 4. Why? When you have 2 variables, the cells will be 2 into n, or 2 into 2, that is 4. Okay, now since the number of variables are 2, the following figure shows two variable k map. So the figure you can see, that is x and z, or sorry, y and z. You have z axis as well as y axis, isn't it? In y you have 0 1 in the vertical way. In the horizontal way, what you have, 0 and 0 and 1 again. So now 0 0 is represented as m0. 0 1, when y is 0, z is 1, that cell is represented as m1. And when y is 1, z is 0, the cell is represented as m2. And when y is 1 and z also 1, the cell is represented as m3. Or you have one more representation there, when you have only one bar, it is something like array, isn't it? It looks like an array. Okay, yz means, so m0 is 0 0, m1 is 0 1, m3 is 1 1, and m2 is 1 0. It is little bit confusing. You can go for the first method itself. The second is somewhat confusing, isn't it? Because it is not in the same direction. So m3 is 1 1 and 1 0 is m0. So it will be little bit confusing if you are starting with the newer step. When you get addicted to it, when you start solving so many problems, then it will not be a problem to you. But now in the initial stage, it is better to consider the x and y, or that two-dimensional matrix kind of box. Okay, the left side one. Okay, now there is only one possibility of grouping four adjacent min terms. Okay, you have to remember the concept of min terms here. In the last videos, I guess I have discussed with the concept of min terms and max terms, isn't it? In the same fashion here, you have to consider the min terms, and you have to group the four adjacent min terms. Okay, so because if you want to minimize the function, you should understand how to group it. Okay, adjacent cells should be grouped, or adjacent min terms should be grouped. Now the possible combination of grouping two adjacent min terms are, when you go for adjacent min terms, what are the possibilities? The possibilities are m0 m1 and m2 m3, then m0 m2 and m1 m3. So that is the possible adjacent min terms, isn't it? You are not diagonal, you are going diagonally. You are not going diagonally. It is just an adjacent concepts. Okay, you have to group the adjacent cells or adjacent min terms, then you will get this particular values. That is nothing but m0 m1, m2 m3, then m0 m2, then m1 m3. So this is how you can get the possible grouping of two adjacent min terms. Okay, now let us see. So this just I have taken this from your textbook. Actually, I couldn't get the separate information from outside, so that is the reason why I have just taken the picture of your textbook itself, that page. Now in figure 3.1 or 3.1, you can see two variable map, the same concept, whatever the things you have seen in the previous slide, m0 m1 m2 m3. But here what they have done, they have represented that values with respect to x and y. So in min terms also we were doing the same thing, isn't it? So when it is 0, it is x dash, and y also y dash. Okay, when the input is 0, but when input is 1, you are not going for that knotting of thing, or what you say, that bar. You don't have the concept of bar. Now how they represented the cells, when x0 y0, then that cell is x dash y dash. When x is 0, y is 1, the cell value is x dash y. When x value is 1, y dash is 0, then it is x y dash. Now when both are 1, x also 1, y also, then that cell value will be xy. Okay, the same thing they have given in their statements. The zeros and ones marked for each row and each column designated the values of variable x and y respectively. Notice that x appears primed in a row 0 and unprimed in row 1. Similarly, y appears primed in column 0 and unprimed in column 1. Whatever the explanation I have given, they have just gone for some standard set of statements. Okay, if we mark this squares whose min terms belong to a given function, then the two variable map becomes another useful way to represent any one of the 16 boolean functions of two variables. So two variables will produce 16 up to 16 boolean functions can be represented using two variables. Okay, as an example, the function xy is shown in the separate figure. We will see the figure later. No, that figure is actually available here itself. Okay, let me zoom in here. Fine. So this is how this is possible. Okay, now 3.2a, the left hand side you can concentrate. So since xy is equal to m3, why xy is equal to m3? In the previous slide also, you can just go back and see the previous slide. There also m3 means what? When x equal to 1 and y equal to 1, isn't it? If you want, I will just let me come back. Just a moment. Yeah, here. So what is m3? M3 is when y equal to 1 and z equal to 1. Just a representation, but in the next slide, what they have gone the variable x and y, but it's okay. But the ultimate thing is when both the inputs are 1, then only you are going to get the value as m3. Here also what they have done, so when xy is equal to m3, because xy is when you are going to get xy when x equal to 1 and y equal to 1. If any one value is 0, then you will get x dash, isn't it? So that is the reason why they said xy is equal to m3. 1 is placed inside the square that belongs to m3. Okay, then similarly the function x plus y is represented in the map of figure 3.b. So you can 3.2b, how it is there, 3.2b. Now you will get 1 1 1. So how you are going to get 1 1, I will show you. So you just concentrate on that formula, x plus y equal to, how you are going to get x plus y equal to what? It is x dash y plus xy dash plus xy. How you got that? When you go for x plus y, you should be going for the the values will be like x dash y plus xy dash plus xy. Now what is x dash y? It is nothing but 1 0, isn't it? It is nothing but 1 0, 0 1. When x equal to 0, y equal to 1, then you are going to get, x dash y is nothing but when x equal to 1 and y equal to 0. Okay, the last but one, isn't it? That x equal to 1, y equal to 0. For the second, xy dash means x equal to 0, y equal to I'm sorry, x dash y equal to x dash y means x should be 0, y should be 1. Correct. So x dash y means x should be 0, y should be 1. When xy dash means x should be 1, y should be 0. Then what is xy? It is nothing but both are 1. When x equal to 1 and y equal to 1, you are going to get xy. So x dash y is nothing but m1, xy dash is nothing but m2, and xy is nothing but m3. How we got m1, m2, m3? By looking at the previous slide or the above one, m0, m2, m1, m2, m3. From there you can get the actual idea. Now what you have to do? You have to place 1 in those m1, m2 and the m3. How you are going to place? You have to go for the same cell and there you have to place the value 1. Now once you put 1, how you are going to get the output as? So you are going to get the output as first cell will be blank, second cell will be 1, third cell will be 1, and fourth cell will be also 1. So that is a representation of functions. So whatever the function you have, you can represent that function in this fashion. Fine. A 3 variable map. Okay, that is the next concept. But did you understand how to represent? So when you have x plus y equal to x dash, there is a one function they have given, x plus y equal to x dash y plus xy dash plus xy. Now they ask you to represent that in that map, k map. How to represent? Based on the values, you have to put the table. From that table, you have to select the cells, and in that cells, based on the function, you have to put 1 in the position of that cell. You have to put 1. Then you are going to get that. So ultimately, that final representation will be the function. So that is a map of that particular function, whatever the function they have given. Okay, so that is the reason why they said that the function x plus y is represented in the map of figure 3.2b by 3 squares marked with 1s. These squares are found from the min terms of the function. So they have they will give one function. You have to find the min terms of that function, and you have to design one table out of which you have to select the cells, and based on that cells you have to put 1, or you have to mark 1. Then only you can get the ultimate idea of this concept. Fine. So this is with respect to two variable map. Now you have one more concept called three variable map also. When you have two variable map, you have this much. When you have three variable map, how many number of cells possible? So it is nothing but 2 into n, isn't it? 2 into 3. Total 6 cells will be available. Correct? So up to 6 cells will be available when you have this one, 3 variable. Okay, now this is how it works. So you can see there a 3 variable map is shown in 3.3. so next slide I will show you. There are 8 minterms for 3 binary variables. Okay, now why there are 8 minterms? Because you are starting from where? So when you have 2n cells, so ultimate cells I am talking, but when it come to variables, when you have 3 variables, you are starting from where? You are starting from m0 to m7. Up to m7 you are going. How? We will see here. Okay, therefore the map consists of 8 squares. Note that the minterms are arranged not in a binary sequence. Okay, it will not be in a binary sequence, but the sequence is similar to the reflected code. Okay, whatever the code they have gone for. So some table concept they have given, but it is not required right now here. The characteristic of this sequence is that only one bit change from 1 to 0 or from 0 to 1 in the listing sequence. So whatever the listing sequence they have gone, there I am talking. Okay, the map drawn in a part B. Okay, I'm just I will move to that particular concept here. Okay, so this is the concept of 3 variable map. So let me continue this concept after explaining this, so you will get the better idea here. Okay, now the number of cells in a 3 variable K map is 8. Since the number of variables is 3, the following figure shows 3 variable K map here. So why it is 8? Because you have to go for 8 adjacent minterms. Okay, it is not just 6. You have to go for 8 minterms. Fine. Now there are only one possibility of grouping 8 minterms. How can you go for? You can go for possible combination would be m0 m1 m1 m3 m3 m2, then m0 m4 m1 m5 m3 m7 and m2 m6. Isn't it? Those many adjacent possible. Next you have one more, m4 m5 also possible, m7 m6 also possible. So up to total how many values you will get? You will get 1 2 3 4 5 6 7 8 9 10 11 12. Up to 12 possibilities you are get, isn't it? When you go for 2 adjacent minterms, you are going to get those many possibilities. If x equal to 0, then 3 variable K map becomes 2 variable K map. How when x equal to 0, 3 variable becomes 2 variable map? Because when you implement x value to 0, then you are going to get only one array, isn't it? You are not going for 2-dimensional, because both the value will be same. You are reducing 3 variable concept to 2 variable concept. When one of the input is 0, I can say like that, isn't it? It is no, not one of the input. When x equal to 0, because it is a vertical concept, not the horizontal one, isn't it? So now what are the inputs you have? You have x. For x you have 0 and 1. For yz you have 0 0 0 1 1 1 and 1 0. Now when x, y, z 3 variables are 0, you are going to get the output as m0. That cell value will be called m0. When you have x equal to 0, yz equal to 0 1, you have m1. The same concept, the previous explanation whatever I have given, same concept you are continuing here also. Now when x equal to 0 and yz equal to 1 1, then it is m3. When x equal to 0, yz equal to 1 0, then it is m2. When x equal to 1 and yz equal to 0 0, you are going to get the cell value as m4. And in the similarly you will get m5, m6, m7, all the things. Okay, now you can ask why m7 before before m6 you have m7? Because all 3 variables are 1 at that time. That is the reason why you are going for m7, isn't it? X equal to 1, y equal to 1, z equal to 1. So last value, that will be the last equation or last value or last constant value you can give for a particular cell. That's why they have gone for m7. In the same fashion you go for m3 also. See, before m2, sorry, after m1 you get directly m3, not m1. Why? Because x is 0 and yz is 1. that is a possibility of getting that value in the almost last, in the last position. So that is the reason why you are going to get that value. So don't get confused. I will explain with example in the next video, don't worry. But this is how you can represent 3 variable k map. Now if someone asks how to represent 3 variable k map, or how many possible adjacent minterms are possible for k map, 3 variable k map, and what are the possibilities, then you have to group like this. What are the points I have given in the above points, the same thing you have to give for 3 variable k map. Okay, so if you have any doubt, you can ask me. And for example, for 3 variable k map, I will make a separate video, because if I explain everything in a one video, then it will be a problem for you. Now you can just imagine this concept. The 3 variable k map also work in the same fashion. You have the same equation you are going to get, whatever the equation you have got in 3.1b. Same thing you will continue with the 3 variable map also. So if you have any doubt, so these are the concepts which I have just now dealt. If you have any doubt, you can contact me. Okay, yeah, thanks for watching. Let me wind up the video here. Thanks for watching.